Great. Okay, so welcome everyone. It's a pleasure to be here. So this is the introduction to statistics for astronomers and physicists, as you can see just there at the top of the page. So everyone should be able to see three windows at the moment. And this lecture today is going to be what I've got here is essentially the course format and an outline of what we're going to be covering over the course of the semester in this lecture. And then the majority of this lecture is going to be sort of a crash course in R and Python for those of you who aren't super familiar with programming. And I'll motivate why we need to do that as well as we get going. So let's get started. As for the other two windows, not need to worry about them right now. You'll see a little bit more about them in a couple of minutes. Great, so I've just copied and pasted here the course philosophy section from Moodle, so many of you will have probably already read about this. But essentially what we're going to be doing in this course, or the idea behind this course, the philosophy, is that it's designed to give you, the course attendees, an introduction to statistics and how in which we use statistics for natural sciences, so for astronomers and physicists, and indeed for chemists and biologists if they were attending as well. And so the idea behind this course is that the idea is that you don't necessarily have to, or you're not expected to have had any previous statistical education prior to entering into this course. Now, the motivation for that is because it's been certainly my experience that in many physicists prior to completing their PhD don't have any formal statistics education. And in the era in which we currently live, where a lot of science is being done in physics and in astronomy, in large surveys using large amounts of survey data and just generally big data sets, be they from colliders or from telescopes, the lack of a basis in understanding statistics is something that we really need to rectify, and something that each astronomer and physicist really should have prior to starting develop during their PhD, their masters, and just overall during their academic career. So the way in which I'm going to be teaching this course, we're going to see a little bit more of over the course of today's lecture. But I want to make it sort of flag at the beginning that you should be expecting that I'm not going to just pull a lot of examples from data sets from astronomy or from physics. I don't necessarily think that that's the best way for you guys to learn fundamental statistical things. I, in fact, think that it's far more useful to draw from experiences that people have, day to day, things that they might have familiarity with, be they something as simple as a coin toss or something as, complicated as a sports league. So a lot of this course is going to be taught using examples rather than things that are pulled directly from physics and physics and astronomy of things that most of us would encounter day to day. And hopefully that's going to be useful for us as we go through. So to give you an idea of what exactly we're going to be covering in this course, again, I've pulled some of this just directly from the Moodle page, so hopefully some of you have already seen this. The first few weeks of this lecture, not including this one in particular, which, as I said, is going to be covering programming, the first few weeks of this lecture are going to be covering how we actually describe data, how we do, how do we characterize a data set once we have it on disk. And how do we analyze it? How do we model it? And basically what we need to do in order to determine some fundamental properties of any particular data set that we might be playing with. And I think that this is something that is just fundamentally very, very useful for anyone working in any natural science or any empirical science even. So we're going to go through, and we're going to start by talking about the different types of data that you can have. And we're going to sort of then talk about how one summarizes distributions of data in terms of, well, how does one data set have some fundamental properties? Like, for example, what is the average of this particular set of numbers, and how do I characterize the spread of a particular set of numbers, things like that. So point and interval estimation. And then we're going to start looking at some more important or some more fundamental things like correlation and covariance. And there's going to be a couple of, very important statistical lessons in there about, correlation, which I'm sure we're all familiar, painfully aware of, in coverage from news and things like that, of correlation does not equal causation, et cetera, et cetera. So we're going to be going through and going through and figuring out exactly what that means and why that's important and things like that. And then we're going to end these couple of lectures by looking at some fundamentals of data mining. I'm using the data mining term there. It's a bit of a buzzword, but essentially looking at how one takes a data set that they know nothing about and quickly and efficiently pulls out the data that is relevant, or the summaries of that data set that are relevant. And obviously, during that process, we're going to be going through talking about how you actually visualize data efficiently and how you plot it, all that sort of stuff. So this is all going to be covered in the first section. The next section of this course is going to be about probability, and this is really where we start to get into the thrust of the statistical parts of this topic. And so we're going to start off by looking at things like decision theory, how one actually makes a decision and what that decision should be based upon in terms of likelihood or lack thereof, something being likely. We're going to talk about the fundamentals of probability, so about what probabilistic distributions are, about why probability is important in the natural sciences. And then finally, we're going to go through and look at a handful of statistical distributions. So these are things like the fundamental distributions that appear in basically all data sets. So these can be things as that you'll all be familiar with already, something like the Gaussian distribution, so the normal distribution that we learn about in grade school, all the way through to distributions that you might not be very familiar with, but which have very, very far-reaching impact in a lot of natural sciences, things like the chi-squared distribution. So we'll be going through quite a lot and looking at that in the probability section. The next section, section 3, is one which is all about what's called Bayesian statistics. Now, if you're not familiar with that term, then don't worry. That's kind of the entire purpose of this section, is to make you familiar with what Bayesian statistics is. But suffice it to say that Bayesian statistics is a different type of probability calculation that is absolutely fundamental to modern scientific inquiry. I don't think it's exaggerating to say that you will use Bayesian statistics almost every single day, whether you know it or not. And so it's very important to understand. And so we're going to go through what the difference between normal or frequentist statistics and Bayesian statistics is. We're going to go through what Bayes theory actually is and how does it come into probability and things like that. We're going to talk about priors. This is a very, very important part of Bayesian statistics. And again, if you're not familiar with that term, don't worry about it. You will be. And then the last thing we're going to do in the Bayesian statistics section is we're going to talk about hypothesis testing. So that is looking at how one actually determines whether or not a hypothesis is correct or is incorrect, and what we can do in order to formalize how we determine whether or not something is true or false. And the last section is on a whole host of different things. I've got it assigned to be sort of the largest of the sections, lasting from week 9 all the way through to week 12 of the lecture course. And that's essentially because while the other 3 sections I think are all important bits and pieces that everyone should know in their academic and scientific careers, the section 4 of this course is really bringing all of that together. It's really why we do all this in the first place. And that is so that we can apply this knowledge. We can apply this, what we've learned about data modeling, about Bayesian statistics, and about probability, and do some really fundamental things that are important to modern scientific inquiry. So one of these things is something like Monte Carlo simulation. Again, if you're not familiar with these terms, don't worry, that's the whole point of this course. Markov chain Monte Carlo, or MCMC. Many of you may have heard of this term. It's extremely widely used in modern science, and I think is something that everyone should have a rough grasp of. And in fact, during this section, I'm going to demonstrate to you not only how powerful MCMC is, but we're also going to actually write up our own MCMC sampler so that I can demonstrate to you just how easy and it's not a complicated tool, the MCMC. But it is an extremely powerful one. We're going to talk about how one accurately fits high-dimensional data. and what that means for modern science when we have typically data sets with more than 2, 3, 4, 5 variables, and we want to be able to distill information from those high dimensional data sets. And so how does one do that correctly or efficiently? And that then links tightly into concepts of machine learning. So this section is also going to go through and talk about sort of the fundamentals of machine learning, give you some examples of machine learning algorithms around things like convolutional neural networks, and how we actually use those. And one of the most important parts of, I think, this lecture course will be in that machine learning aspect, where we learn what not to do with machine learning, because machine learning is very, very popular at the moment, and it's being used as sort of a scattergun to attack every problem in science. And there are some things that you must know prior to doing that. So these are what we're going to be covering in the course. Hopefully that all sounds very interesting for you all. I know it certainly interests me, otherwise I wouldn't be here. I'm going to spend the next couple of slides talking to you about how I'm going to be presenting this course. So obviously, given the situation that we're in, we're not sitting in a lecture hall just in front of a slideshow and a whiteboard, but I'm doing my best here to try and keep that sort of feeling of being in a lecture hall with sort of a bit of back and forth alive, and we'll see how that is in a moment. The way in which I'm going to present the material in this course is using this window you can see here on the left. And that window is essentially just a presentation that has been constructed using this thing called R Markdown. The reason for using that particular format, R Markdown, is not hugely important, except to say that the main motivation for me is that many people in science, in physics, in astronomy, and in other sciences, program their analyses and they do their science day to day in one of two languages, one of which is Python and the other of which is the statistics language called R. We're going to talk about those both in a second. But the utility of R Markdown is that I can utilize both of those languages at the same time. So I can have, for example, in this slide, like I've got here, I can take a chunk of R code, which plots a sine wave, which is what's being showed here. And I can, just write that code as an example to you. So we'll get into what this actually means during the latter part of this lecture. But so I can produce a snippet of code and then run that code in the presentation. And I can do exactly the same thing with Python side by side. And that's really useful because it means that we can use this R Markdown format in order to create examples that are able to be understood by both groups of people, because people tend to learn either R or Python. We'll get into more of that a little bit later. One of the other things that's really useful about R Markdown is that not only can you run these snippets of code side by side, so it's a little bit more fancy than just having, for example, a window here which has an R terminal in one side and a Python terminal in the other. What the R Markdown gives you is also the ability to crosstalk between these two sessions. So I can generate some data in my R script here, and then I can reference that data for a plot in my Python snippet here as well. So this is just to show you the motivation for using this particular format. And if all of that wasn't terribly clear, don't worry, we're going through and talking about R and Python in a lot of detail over the course of the next 2 hours. The next thing that I wanted to talk about was what this little blue square is at the top here. Now, this is a thing called Slido, and this is the way in which I'm going to be sort of using, hopefully getting you guys engaged with the lecture, so that it's not just me sitting and talking to you at length for some time. And it's great to see that I've already just seen that there's already a bunch of you who've joined the Slido. And so what Slido is you can scan this QR code just with your smartphone, or you can, on your computer, you can go to slido.com and put in this code at the top of the page. And what Slido is very, very useful for is it allows you guys to give questions to me in real time, just as a simple prompt. And also I can use it to have polls and things of you guys. The main thing that I wanted to get across with this particular slide is that it's really, really beneficial for all of us if you guys ask as many questions as you can. And so there's a couple of things that I wanted to mention that sort of make this a little bit easier. The first of which is that you can ask questions anonymously. And I encourage you to do so if you're apprehensive about asking questions and putting your hand up. If you're not the type of person who would normally put your hand up in a lecture and ask a question, this is the perfect forum for you to ask questions, because you can do so anonymously and without having to worry about often in real lectures, people tend to start their questions with the phrase, "This might be a stupid question." I'm one of those people. You don't need to do that here, because you can freely ask these questions without worrying about judgment or anxiety. There's no anxiety here. All questions are good questions. There is no such thing as an irrelevant or an unneeded or a bad question, because the whole point of this is that you are demonstrating that you need some more information on something. And I don't want you to feel like you should be reserved in asking questions. The reason why it's very useful for us to have lots of questions in Slido is because once a question is registered, everyone can add support to that question by giving a little thumbs up. So I can give you an example here using my little Slido. So I can say, "Is this a question? Question mark, send." And what you'll see is that this little question then pops up on the Slido. And now what people can do is they can click on the little thumb here, as you're all doing, and that question will then float to the top. So the way in which Slido works is the most popular question floats to the top. So what you should do is you should think of this as the little thumbs up is your way of saying, "Oh, that's a really good question. I'd like to know the answer to that as well." And so you click the little thumb up, and then I'll see that, and I'll see that lots of people would like to know the answer to that question, and I'll answer it. Now, of course, I'm going to try and answer every question that appears. But if there are lots and lots of questions, the questions that are popular will be at the top and they'll get answered first. So it's really useful for everyone to ask questions and to use that little thumb up. It really, really should make this a lot more engaging for all of us. And most importantly for me is that when you guys ask these questions, I'll be able to look back on them after the lecture and say, okay, this part of the lecture was clearly unclear. And so I need to do more work and improve the lecture notes or improve the slides so that when I deliver the slides and the lecture notes to you guys, the right amount of information is where you need it. So by giving me feedback and by asking questions here, the course notes will better cover the things that you don't understand or you need more help understanding. The course is going to be more relevant to you because the questions you ask will be the things that are relevant to you. And of course, the course is going to improve over time, which helps everybody involved. So basically, what I've been saying for the last 5 minutes is please feel free to ask questions. Please ask your questions. And then once they're done, I'm going to come over here and I'm going to go, yep, that question's been answered. And that's all there is to it. Great. So as you saw on the title slide, this lecture is going to be covering a lot of statistical computing, or a lot of programming rather than statistics for this first lecture. And so I'm sure some of you are asking the question, why? Why do we actually need to know programming in order to know statistics? And while of course, as I said, it's entirely possible for you guys to learn statistics with a pen and paper. That's totally fine. That's totally how a lot of people have learnt their statistics. However, I think given that this course is about learning applied statistics to the academic career that you guys are going to have or currently have, it's important that you not only learn the fundamentals of like the equations and diagrams and things like that. It's also very, very useful for you guys to learn how you apply these methods to real data sets in real life. So that's essentially what I'm saying with this little code block. So there's a question here: will I upload the lessons to Moodle or just the lecture notes? So it's a trick question, because the lecture notes that I'm showing you here, these slides, are actually the lecture notes as well. That's why you'll at times see large-ish blocks of text that I'm not super happy about. But if people think that these large blocks of text are distracting, then I'm happy to create lecture notes and slides. But I think this is hopefully going to be more useful for us as we go through. But I'll upload the lecture notes, and if there's enough requests, then I might also be able to upload these recordings if people are interested. Now, I'd prefer to just keep these for myself, because I'm averse to people having to just watching the lectures, because if they just watch the recording, then they're not engaging with, for example, the question and answers and stuff like that. They're not going to get as much from the lecture. But of course, if people say that would be really useful, then of course I can do that. Great. I'm going to click that as answered. Yes. So the question sort of says, why do we need programming? And I'm going to give you a really sort of what I think is a great example of why programming is really, really useful, why it's really useful for statistics, and why it's really useful for empirical sciences. And I'm going to do this with an example. So in 1941, this guy called Erich Holmberg here, sorry, my window was just in front of his last name, performed an experiment where he looked at a simulation of colliding galaxies. And this was 20 years before what's now been known as the paper that begun the study of what's called n-body simulations, where you simulate a whole field of massive particles and you smash them together on a computer and you say, what happens? And so this first paper that was on n-bodies was by Sebastian von Hörner, and this was published in 1960, whereas Holmberg's paper came out in 1941, and what Holmberg was able to do was able to take all of these different particles of, say, two galaxies, which here are rotating, say, clockwise or counterclockwise, and smash them together and look at what happens afterwards. And what he found was that you get these really long features that have since been become known as tidal deformations. It's in fact what he says in the caption, tidal structures. And what's really amazing about Holmberg's work isn't so much that he developed these, was able to find these tidal features that we now see in computational n-body simulations, like what you can see here. The really amazing thing about Holmberg's work is that he did it entirely by hand. So what he did was he took an arrangement of light bulbs, which were arranged in a fashion like this, and he put them on the laboratory floor, and he put another set for the other galaxy, and then using a photometer, calculated the amount of light at every position within the galaxy that was being illuminated by this galaxy and the one next to it, and used that to compute the gravitational potential that was being felt by each one of the light bulbs. He would then go down to the floor, step the entire interaction one step forward, and redo the computation. And doing this entirely by hand, he was able to reproduce some of these features for the very first time. It's really, really amazing stuff. But the reason I'm showing you this isn't because that is an amazing amount of work and an amazing achievement. It's because doing what he did painstakingly by hand is now something that you can do with your laptop in about a minute, or rather on your smartphone in about a minute, if you really, really wanted to. So while you can do these things by hand, doing them computationally allows you to both be more detailed, because we are able to scale this thing up massively. It allows it to be more reproducible, because I can say to you, here's my piece of computer code. Can you run it and make sure you get the same thing on your data set? And most importantly, it allows you to be more accurate. Right? And that's something that we're going to be talking about quite a lot, because when you do these sorts of things by hand, there's a lot of possibility for errors. So as an example, why is it that we need modern programming beyond just saying, okay, obviously we don't work with using light bulbs on floors, right? That is not something that we do on a daily basis. It's not something that we expect to come up during our academic careers, understandably. The question is, why still do we need it even now? And I would say that because of the nature of modern science with large complex data sets, we expect those large complex data sets to be analyzed with modern methods. So a classic example of this is optimization of a model. So let's say I deliver to you a data set. That data set is these blue dots here. What I tell you is that that data set follows some, y value, which is, a function of the x value, and follows what's called a beta distribution. So that beta distribution has some arbitrary shape. And the beta distribution is governed by two parameters. We'll call them alpha and beta. And I've told you that alpha and beta can be anywhere between 0 and infinity. So the question becomes, how do you figure out what values of alpha and beta are the ones that fit this model best? Now, in your high school, the very first thing that you will have been told, and indeed the very first thing that most of us would say in this first thing, is, well, let's just guess, right? And this method of just guessing and checking the result and saying, well, that doesn't really fit very well. Let me try this value, and let me try this value, and let me try this value. This method used to be very, very popular in science for model optimization. And I argue, and I would argue, and I think it's not unreasonable to argue, that this is entirely inappropriate for modern science. Now, what you can see here is an example of guessing and checking. So we're basically randomly guessing alphas and betas, and we're looking at the fit parameters here. And you'll see that as we go, well, that doesn't fit, that definitely doesn't fit, right? Oh, look, 2.9, 5.7. That's not too bad, right? And so using this guess and check method, we can get a fit that's, well, let's say, okay, we guess and check and we iterate a bunch of times and we say, okay, there we go. We're going to stick with 2.8 and 6.7 as our best fit parameters for alpha and beta. The question then becomes, is that right? Or not even is that right, but is it consistent with the truth? And the consistency is kind of the important thing, because the thing that this guess and check method absolutely doesn't provide you with is any sort of measure of uncertainty. It doesn't give you any sort of measure of how close or how consistent is my model with the data. Because your guess and check, your human brain is fundamentally incapable of figuring out whether or not something is roughly good or good enough. Right? It's just not something that our brains were designed to do. Now, the reason why I think that this is an utterly untenable thing to be doing in modern science is because I can do the correct thing in one line of code, right? And we can do the correct thing in one function. So here I've got two snippets, one in R and one in Python. And what I'm doing is I'm fitting a model. Now, you don't need to know the details of what I'm doing here. We'll cover this in a later lecture, but suffice it to say that this is fitting, this is fitting a beta model for alpha and beta, the things that I'm trying to fit. So here, alpha and beta, to my data, X and Y. And I do the same thing in Python. I fit a beta function with X and Y to my alpha and beta. And what you get out of R is that the best fit alpha and beta are 3.21 and 7.71. Now, the first thing you notice is that this is vastly different to what we had in our guess and check method. So guess and check was nowhere near the correct answer, it turns out. Python gives you the same answer, as you most certainly hope it would. And so obviously the fits themselves are actually superior, but the main reason that this is beneficial, the main reason this is relevant and important, is because it comes with a measure of uncertainty. Yeah, that's a very good question. What exactly is a beta model? So a beta distribution is just one of these statistical distributions that we're going to talk about quite a lot at length a bit later on. So like I said, you can basically just think of me having given you an arbitrary cloud of data points and said that this is the functional form of it. It would be equivalent if I gave you a quadratic equation, for example. So the exact function at the moment isn't super important, but it turns out to be an important distribution. So it's a good question, but we'll cover it much more in the probability distribution section of the course. Cool. So the main thing that comes out of the model fit is uncertainty estimation, right? Is a measure of how good the fit is, how well I've constrained these different parameters. And here you can see, if I just look at the summary of the fit that I made in R, I get out the estimate, which was the thing that I was looking at with my guess and check, but then also a measure of uncertainty. So this standard error. And it turns out that the fit, given the data that I have, is accurate to 0.01 in alpha and 0.04 in beta. Now, again, it's not super important to worry about what this means, other than to say that what we did with the guess and check method, if this is the actual correct result, was catastrophically wrong, right? And even if it wasn't, it doesn't come with a measure of uncertainty. And it's a fundamental thing that we need to be able to do in modern science. And you can do exactly the same thing with Python. This is just to say that you can do the same thing with Python. You can get the same results out. Okay, so we've spoken quite a bit about R and Python. I'm going to spend basically the rest of this lecture going through a crash course in what you do to program in R and Python. But first, I think it's worthwhile asking the question, because I'm sure many of you are asking the same question to yourselves: do I need to know R, or do I need to know Python, or do I need to know anything else? So the first, now let me just see. Yeah, so there is, I think that there is sort of one main reason to pick a particular programming language over another when learning about how to learn a language. So here I'm gonna launch a little poll here, and the poll is: what is the most important consideration to you when picking a language to learn? Right now, so what you can do is you can go onto Slido and you can just put in a word or a sentence or whatever that tells me or us what you think the most important thing is, the most important consideration when learning a language. Now, I've intentionally said language, not programming language. It's because I think that a programming language is not dissimilar from a regular language in terms of how you learn it. So this could also be true of learning French, for example. Okay, we've got 2 responses so far, so I'll let people keep on putting in responses. So, like I said, I think that there is essentially one major consideration that you should have. So I'm curious to see how what people think with regards to their answers. All right, so we've got a few responses in there. Let's have a look at the responses. Okay, so we've got good online tutorials, can do with, well, that's obviously important. So it's broadly applicable, useful for future applications. Does it help? Is it easy and practical? Is it used in the field of interest? These are all really, really good points. However, I would say that there is one overwhelmingly relevant question that needs to be asked for determining which language you are going to learn to use. And that is quite simply, what language do your colleagues use? So if you are, I mean, the silly way to think about this is that if you're going to work in France, learning Italian is probably not going to be very useful, because when you get to France and then you start speaking Italian to your colleagues, they're not going to necessarily know what you're talking about, right? So it's the same thing with a programming language. It's very, very useful and important to have the skills that allow you to communicate efficiently with your colleagues. So if it turns out that the vast majority of your colleagues code in Python, and by colleagues here, I'm talking about your fellow students, your postdocs, supervisors, your professors, and things like that. If they all use Python, you should learn Python. If they all use R, you should use R. If they all use MATLAB, you should use MATLAB, right? Like, this is, for me, the overwhelmingly important thing, because it means that you'll be able to communicate and engage with your collaborators better. Hopefully that kind of makes sense. Okay. So for me, I think that, yeah, as I said, you should just focus on whatever suits you best. With regards to R and Python, I think that the majority of physicists and astronomers now are using one of these two. Most of them are using Python. There are differences, perceived benefits and detriments from both languages, but I'm going to show you that overwhelmingly these two languages are basically equivalent nowadays. So the first thing that's worth asking is, what's the difference, right? So R was originally developed as a statistics data language. It was developed from a language called S. It's not a joke. And the language S was essentially a statistics data language that was proprietary, so you had to buy it. And so two people whose names both began with R decided to write a free version of it to start. And so that's where R was born from. And it has lots and lots of additional tools that you can buy, that you can download. They're all obviously free on the Comprehensive R Archive Network, or CRAN. And one of the utilities that we'll see a bit about later is that they're all required to be fully documented. And so that means that basically, if you want to do any sort of statistical analysis, there's a very, very good chance that well-documented packages to do it already exist in R. Python, on the other hand, has the primary strength of being that it is a general programming language. R is a statistical analysis data language that can be used for writing programs, absolutely, but Python is primarily a programming language, and a programming language that you can then use to do statistical analysis. Python has lots of packages, and I've given an example here available via Conda, but you can obviously download them elsewhere from, we'll see in a sec. And they're generally very, very reliable, because they generally have gone through a lot of vetting. Now, as you'll probably notice, I primarily code in R, which is useful for this course in particular, because obviously we're going to be doing a lot of statistical analysis. And so with a lot of statistical analysis, as I said, there's lots of tools to do that in R, and it's very, very useful. However, it's very, very easy and possible for us to redo much of the analysis in Python. And indeed, for the rest of this course, or this lecture rather, I'll show you basically both side by side. In practice, I'm going to be doing a lot of R in this course. So I'm kind of hoping that this lecture will give those of you who are most familiar with Python, will give you essentially a sort of Rosetta Stone to figure out how the R code converts into Python code. For those of you who aren't familiar with either language, then we can go through and talk about, you'll hopefully get an idea of how both languages work. But I'm happy to rewrite examples that I've written solely in R over the course of this lecture in Python, if you think that would be useful. So you just simply need to give me that feedback and say, hey, this would be a really good function to know how to use in Python, and I'll happily write that. Great. So one of the things that you'll notice, hopefully over the course of the rest of this lecture, is that basically if you can read and understand one, you can read and understand the other. They're not super dissimilar in a lot of ways. So as we'll see, so we'll get started. So I'm going to give you sort of the rest of this lecture now is going to be giving you sort of a crash course in Python and R. But I wanted to start off by giving a quick poll to give myself an idea of what sort of level of experience everyone here has with programming languages, with programming. So I've got here, what level of previous experience do you have with computer programming right now? And I've given you 10 possible responses. Those possible responses are 0. I'm currently listening on my Nokia 3310. For those of you who don't know what a Nokia 3310 is, please keep that to yourself, because it'll make me feel very old. 1, I've heard that people use computers for programming, but that's it. 2, I've read about programming, but that's it. But I've not tried it myself. 3, I've written hello world programs before. So I've written the very basic hello world programs. 4, I know what Stack Overflow is. 5, I've coded occasionally in 1 or more languages. 6, oh no, it's sorting by popularity. I'm confident that I can write basic code without too much Googling of syntax. 7, I have considerable experience with programming in one particular language. 8, I have considerable experience with programming in 2 or more languages. 9, I'm a faculty member in the computer science department. How did I get here? And 10, I'm the architect. I've been expecting you. For those of you who are familiar with Matrix. So it looks like we've got the majority of people are sort of 6 and 7, and then a bunch of people with 3 and a smattering around there. So this is great. This is really good. I wasn't I was totally unsure of whether people would be coming in here with absolutely no familiarity with the codes or with programming languages. So it's great to know that you guys have got basic code understanding for some of you, or considerable experience for some, or have just tried like coding before. But it looks like the majority of people, and in fact nobody has selected the I know very little, which is excellent. So that's going to be really useful for us going forward. Okay, thanks for doing that, guys. That's really great. I'm going to close that poll now. Okay, so as I said, there are lots and lots of, we're going to be going through for the rest of this lecture and talking about sort of a crash course in R and Python. There's lots and lots of online tools that you can use to learn R and Python yourself if you want, and if you haven't done so already. You'll be seeing a lot of R and a lot of Python in this course, as I've already said. If you're already familiar with Python, then this will be sort of a Rosetta Stone, as I've already said. There's a couple of important NBs, so nota benes, for this rest of this lecture. So the first of which is that a lot of what I've written here focuses on simplicity rather than efficiency or elegance. So if you're a seasoned Python programmer in particular, then you are likely to be very upset with some of the simple code that I've written here. However, I think for those of you who aren't familiar with it, it will be very, very easy, hopefully easy for you to follow along. There may be other or better ways to perform the operations that I'm showing you below, and if they are, please just let me know. This is essentially a list of things that I think are good and important to know, but it is certainly not exhaustive. So there are certainly things that I don't talk about here that you might want to know. And the last of which is that you can always learn more R and Python, especially advanced operations that I don't cover, using this very useful website. Let me just click on the very useful website so you can see, yeah, there it is, right, Google. No, all seriousness aside, that is a very, very useful thing. I mean, like I said, there are so many tools for learning R and Python that if you want to learn more about it, then it's very easy for you to do so just by Googling around for syntax. The second, or the latter thing, is that I am certainly not a Python expert. So while I'm familiar with Python, and I like to think of myself as a competent Python programmer, I'm certainly not an expert. So if there are Python snippets here that you think are less than optimal, then please just feel free to let me know, and I'll happily update them. Okay, so in the following slides, this is what we're going to be covering. Oh, we're actually not going to cover that last point. So we're going to be covering the assignment of variables, different variable types, different data types, code structures, how we do indexing, loading and installing libraries, reading and writing data, and plotting. So hopefully this will give us just sort of a buzz overview of all the things that I think are important about programming and how they sort of come into the languages. Okay, so let's get started. Now, remember, if you have any questions, feel free to ask on Slido. I'm going to, I'll try and do my best to finish my thought prior to answering your question. So please don't think that I've ignored your question if it pops up. It'll also give other people an opportunity to give a thumb up before I get to it. All right, so the very first thing that we need to know about running and using R and Python is essentially how you install and load different libraries in. Because as I said, lots and lots of different libraries are available in both languages for download and for use. And a lot of them, especially in Python, are very important to just being able to do all of the fundamental sort of stuff that we're going to be doing. So the way in which you install packages within R is using this install packages syntax. So this is from within an R session. So you launch R by just typing R on the command line, or Python by typing Python on the command line, and you install packages from within R by just using this install.packages and then the name of the package that you want to install. So here we're installing a package that's called remotes. And the reason we're installing remotes is because it's going to be very useful in about 15 seconds time. In Python, the main way in which we install programs is using this thing called pip, or pip installs packages. It's a recursive acronym. And it's the syntax is simply just pip install and then the name of the thing that you want to install into Python. And this thing that I'm installing here, NumPy, is one of the things you're going to be seeing an absolute huge amount of over the course of the next hour and a half, or in 15 minutes. To load a package once it's installed in R, we use this library command, which essentially just says I want to load this library into the session that I'm currently in. And so we load library remotes in. And similarly in Python, we have this thing called import, and import NumPy does essentially brings the library NumPy into the environment that we're currently working in. This additional bit that's on the back here as NP means that you can then access the library that is NumPy using the shorthand NP instead of using the full text NumPy. Now that's really useful because, as we're going to see, Python is tended towards this thing called object-oriented programming. And so this NP actually gets called a lot. And so if you have to type out NumPy every time, it becomes a bit laborious. So they use NP for short. But you can rename it whatever you like with this as syntax. You could call import NumPy as Frank if you really wanted to. It's totally up to you. Once you've installed, so here I'm just giving you another example of installing from somewhere other than pip and from CRAN. So when you use this install packages, it automatically searches for that package on the Comprehensive R Archive Network, CRAN. But if instead we want to install something from, say, GitHub, then we can use this remotes library, which I just mentioned, which has this function called install_GitHub. And then all we do is we just give it the user and the GitHub address of the thing that we want to specify, that we want to download. So here I'm installing the rfits package from the user ASGR, who happens to be my PhD supervisor. And conversely, what I've done here with pip is if I want to install install something from GitHub, then you can do it using this simple syntax where you say git plus and then the URL to the thing you want to install. So that's again, it's hopefully pretty self-explanatory. So we have a question here asking when you need to specify pip3 and why. So pip is actually, when you install Python, pip is actually a soft link. So it's not actually the binary thing that you want to call itself. It's actually a pointer to something else, which is called either pip3 or pip 2.7. And that comes from the two different versions of Python that are most prominent, most commonly used. When for the vast majority of this course, whenever I say Python, I mean Python 3. Whenever I say pip, I mean pip 3. And you can just use Python and pip to reference Python 3 and pip 3 on most modern computers when you install Python and pip, because the pip 3 overwrites the pip 2.7, for example. But to give you an idea of what I mean, so here I'm just back in my terminal. If I close this session of Python, if I were to type Python 3, I would launch into the exact same Python as I launch if I say Python. No, I don't. I lie. If I go into Python, I launch Python 2.7. So there you go. I was wrong. We'll do it live. Anyway, so that's the main difference. So when you call Python, and it's actually a very good point, when you call these things without the postfix of the number 3 or 2.7, then you're basically at the mercy of which one of these 3 or 2.7 appears first in your binary path. So it's usually a good idea to say 3 and pip 3 and stuff like that. So that's a very good point. I will update these slides to explain that more. Thank you for the question. Okay. So the next thing that's worth discussing is just sort of the structure of code. So this is how the programming languages differ. One of the ways in which they differ, and that is that R and Python differ in terms of the way in which you actually format and structure your computer code. And the main reason is because R imposes a code structure through the use of curly braces. So that is to say, if I want to write an if statement, so this is a logical statement that says, if this condition is true, do this bit of the code, otherwise or else evaluate this bit of the code. And this is very, very useful that we use a lot in programming. And the way in which those code, that separation between the true condition and the false condition is imposed is with these curly braces that you can see here. And this follows, if people are familiar with another language, which is called Lisp, which is very, very heavy on curly braces. And that's sort of the similar sort of syntax that R uses. Python, on the other hand, imposes code blocks using indentation, using white space. So this if statement, so it's the same thing as we've got over here. We have if this condition is true, evaluate this code block, otherwise or else evaluate this code block. Now, what you'll notice is that there's no braces here. Instead, the code block itself is determined or is dictated by this tab, by this indentation here, and it becomes really important. There's also different forms of conditional statements in R and Python. So the 3 sort of big ones are if, for, and while. So the for statement says, for some variable within a particular sequence of variables, I want to do this, right? So it's essentially a loop, and you have the same syntax. It's almost exactly the same syntax in Python, just with a different choice of whether you have brackets or indentation. And the next thing is the while statement, and the while statement does exactly what it says on the tin, which is that while this condition is true, it continues to loop through this particular code block until you end up with something that is false. And when that hits false, then all of a sudden it throws out to the rest of the code, to below that code block. And you have the same syntax again in Python. So we have a question, which language is recommendable to somebody who knows a little C++? So one of the great things about Python and about R is that they both have the ability to use C++ and C natively within them. In fact, R in particular has essentially a C++ spine that you don't see and you never actually interact with, but the overwhelming majority of programs and functions in R are actually written in C++ in the background. So if you are familiar with C++ code, it's absolutely trivial to use that C++ code exactly in line in R using a thing called the R C++ package. I haven't talked about that here, but I have lots of notes about how you actually do that, and it's very, very easy to do. So if that's something that you're interested in, then that's very easy to do in R. I'm certain that it's also very, very easy to do in Python. So it's one of the reasons that these languages are very similar is that, like any good modern programming language, it's extremely diverse with how they interface to other languages. And that's why one of the reasons that we talk about a bit later, which, you can use R to run Python code and you can use Python to run R code, right? These things are all very, very interconnected. So there's no obvious answer, I wouldn't say, to which one is better. the indenting syntax is more of like a Fortran-y sort of thing, but a lot of the conventions that they use in Python is C conventions that we'll see in a bit later. So there's probably no obvious answer, to be honest. So one of the things that I wanted to show about why the differences, or what the difference between the choice of curly braces and indentation means for R and for Python is that one of the things that the indentation imposes upon the user in Python is basically a very strict format for how you construct code. That doesn't exist in R. So for example, if I wanted to create a valid nested loop that basically says I create a matrix, we'll talk about these in a second, and I want to make the upper corner of my matrix all set to 1. So what I do is I use this for syntax, and I say for every column in 1 to the number of columns, and then for every row in 1 to the number of columns here, I want to set that entry row column to 1. And this is a totally valid loop, a nested for loop in R, and it ends up with this. So you end up with everything set to 1. You can also do it without brackets in R. So you can do for row matrix, and here I'm setting it to 2, and that works. However, and this is a big trap, it only works for 1 line at a time. And so if you had a silly mistake assignment in there, then you would end up with just the last entry being given as the number 3, right? So in general, while this is valid syntax in R, generally go crazy with the brackets because it doesn't hurt and it helps avoid bugs in R. This is also a valid for loop in R. It looks atrocious and you should never write it. But my point here is to demonstrate that there is no like white space indentation syntax. Even though I always tend to give these indentations, there's absolutely no reason that they are necessary. So this is a totally valid loop in R. But please, for the love of God, don't write loops like that. In Python, there is exclusively one correct way to do this. You can only do it like that. That is to say, you have to indent at the first 4, you indent at the next 4, and then you have the assignment. And then here, that because there's no indent here, that closes the for loops, right? And so there is only one way to specify this correctly in Python. And many would say, and I personally agree, that this is a strength of Python because it prevents people from coding in horrific manners, which is entirely valid within R. So, this is an important thing to consider. It's a nice thing to consider. And you can see that we end up with the upper quadrant here, all set to 1. Cool. Yeah, I agree. We have a note that says, since we're answering questions in the lecture, I think it would be useful to upload them. So I think that's probably a fair statement. So yeah, thanks for the feedback. I'll pin that. Okay, so the next thing I want to talk about is built-in functions. So this is a pretty important part of the programming. I apologize in advance for this very, very large block of text. Don't worry, you don't have to read it. This is more for the lecture notes part of the thing. What I wanted to get across here is that there is because R is primarily designed as a statistical program or a statistical analysis language, there are many, many things that are available within base R that basically do all of the things you could possibly want. The corollary is in Python, where Python is not a statistical data analysis language. It is a programming language. It is, C or Fortran or C++, right? And because of that, in order to access a lot of the functionality that we would use just natively in base R, we have to load in packages. And those packages are why you're going to see lots and lots of things like NumPy, import NumPy at the beginning of scripts and things like that. There are other packages that you'll see a lot of in this course, one of which is called SciPy, so Science Python, and the other is called AstroPy, which we'll use for the few examples that we give about astronomy specific things. Great. Most of scientific Python programs are going to start by importing one or more of these packages. It's just something that you're going to see a whole lot of. A great example of this is what we were looking at earlier with our beta distribution. So a beta distribution, as I said, is just a statistical distribution. What it is not super important, but it is a fundamental thing to statistical analyses. And because of that, it is a native function in R. So you can access the documentation for any native function or any function that is loaded in using this help command, or alternatively, you can actually just use a question mark at the beginning. And what it does is that launches a documentation page for R. And that documentation page has lots and lots of stuff in it. So I'll show you very quickly what that sort of looks like. Let me go to a console here. So this is an R console, an R terminal. And if I just do question mark D beta, then I launch this thing here, which is the beta distribution help page. And there's lots and lots of documentation here. There's lots of stuff, right? And so what these documentation includes is it includes a function description. It includes how you actually use the function. It includes the arguments that go into that function and what they mean. So remember, we were using these alphas and betas. And so they are called shape1 and shape2 in this function. And they're the non-negative parameters of the beta distribution. You have detailed information about the different functions that are associated with that particular thing and how they are used. You have notes about possible errors and ways in which you can go wrong, and that's super useful for finding problems, rather. Super problem, not what I meant to say. There's authorship and citation information, which is good if you want to be able to give people credit about stuff that you're using. There's references if you want to read more, so references frequently to statistics literature and things like that. There's a list of related functions, and overwhelmingly the most important is that there are examples. And the examples then lead me to the next built-in R that is really useful, which is just called the example function. And the example function is super handy because it basically just executes all of the examples that are present in the analysis, in the package. So we can go back to our terminal here, back to our console, and let me minimize this and that. No, not that. There we go. And what we can do is we can say example d beta, and what we get is all of the examples get run, and also it shows a bunch of plots, which hasn't shown up because I'm running two different things at once. So we won't worry about that for the moment. You can also do this in Python. So Python also has this help syntax, which, for example, we've now looked at the beta function, which is not native in Python. Instead, it falls into the SciPy stats package, and you get a similar sort of thing. You get the information about the function itself, what it does, how it's used, the arguments that go to it, and different attributes and things like that. So there's lots of information that you get from both R and Python, which help with how you use functions and things like that. So it's good to know these sorts of inbuilt functions. They're very, very useful. Okay, so here we're going to go into some of the fundamentals of actually programming in both of these languages. So let me just have a quick look at the questions. How are you sure R packages are good, or is it possible that some of them are not validated at all? No. So one of the great things about the R packages is that they're all validated prior to arrival on CRAN. They have to have a bunch of unit tests and things like that that go into them. And additionally, they're written overwhelmingly by statisticians. They're not written by astronomers. They're not written by physicists. They're written by people whose entire careers are based upon these sorts of modules and processes. And they're extremely highly vetted. Usually, they're published prior to being approved to go onto CRAN. So for example, like with the d beta that we were just looking at, let me go back to the help. So you can find, if you scroll down here, so as I said, there's citation and reference information. So this function was actually inherited directly from S in 1988. And all of these sort of functions show you where these functions came from, how they're implemented, and they have unit tests and things and the examples that show you how they're used. They also have history about how they were implemented. So the P beta uses a C translation, and it comes from this paper, and et cetera, et cetera. So there's lots and lots and lots of information about how reliable these things are, and they're widely vetted before they arrive on CRAN. And CRAN routinely kicks out packages that aren't kept up to date. So the only things that are available on CRAN are things that are updated consistently every year, basically, or verified, re-verified every year with the updated R releases and stuff like that. So it's very, very highly vetted. Yeah. Cool. I'll answer the question for after the lecture. So variable assignment. Okay, so this is one of the most simple things that you can do in any language. So we have, let's say we want to set a variable to the value of 10. We just do a equals 10, and equivalently in Python. Pretty easy. If you want to do addition, b equals a plus 4, b equals a plus 4, and then we want to print the result of that, we just do print b. So the syntax here, as you can see, is exactly the same. More traditionally in R, the syntax doesn't use the equal sign. Instead, what it uses is this funky arrow. And the reason that it uses that is largely historical, but what it means is that I can rewrite this like this. A arrow 10, B arrow A plus 4, and I get exactly the same result. Okay. The arrow notation, as I say, is mostly historical, but there are some reasons why it still exists, most of which you don't necessarily need to know about. However, it's worth knowing that the arrow exists, predominantly because you're going to see a lot of it. And we'll explain why in a second. One of the things about the arrow, one of the ways in which the arrow differs from the equal sign, is that the equal sign assumes that you're always assigning right to left, whereas the arrow sign assigns along the direction of the arrow. So it's entirely possible in R to do that. 10 is arrow A and A plus 4 is arrow B, and you end up getting the same result. Now, it's worth noting that you will never use this functionality because it's extremely unlikely that you're ever going to want to start changing the way in which you read assignments. But it's worth noting that the direction of the assignment is explicit with the arrow, whereas it's not explicit necessarily, with just the equal sign. Or it's not obviously explicit with the equal sign. The main problem with the arrow is there is one catastrophic common failure that happens in R code and people who are writing in R code for the first time, and that is that the arrow A arrow 3, or rather 3 arrow A, assign 3 to A. If you put a space in between the hyphen and the less than sign, then all of a sudden this doesn't say assign 3 to A, it says is A less than -3. And that will cause all sorts of problems in your program. So important to make sure that there's no white space between the arrows. So that is the main reason that people tend to preference using the equal sign. Although, like I said, there are reasons that they are different, and the main thing is because of the way in which it's used in functions, but it's not hugely important for us to know right now. For new users, and especially those of you who are going to be who would be flipping between R and Python, it's best just to use equals. Don't use the arrow sign. It'll just open a whole world of problems. I, however, as you're going to see throughout this course, use the arrow sign very, very heavily, and that's essentially just because that's how I was taught. I learned R from some very picky R purists during my masters, and I just never broke the habit. But full disclosure, this means that very frequently when I'm writing in Python code, I accidentally use the R assignment and things go absolutely crazy. 2 out of 10 would not recommend. So I highly recommend that you stick with the equals notation if you're not already very, very fluent with R. Cool. How do we define functions? So functions are going to be really important, especially in R, but they're really important in Python as well. And the way in which you define a function in R and Python is slightly different just in terms of the syntax. So in R, you define a function named here, we're defining it called the root mean square, RMS. And the function takes variables A and B as inputs, and it returns the square root of A squared plus B squared. Okay, similar sort of syntax in Python, except instead of assigning, you define functions and you define them with this syntax of RMS and then what that variable takes. Obviously the indentation, very important, and it returns the numpy square root of A squared plus B squared. Now, one thing that we're going to talk about a little bit later is about this caret versus the double thing. It turns out to be important. And so what this means is that then we can define two vectors, so two arrays of data. So a sequence from 0 to 1 of 10 elements, or a linear spacing from 0 to 1 of 10 elements in both R and Python. And then we can calculate the RMS of X and Y in both languages, and we get two results out that are exactly the same. So that's how you define custom functions in R and in Python. Okay, so the variable types in R and Python are pretty important. So in R you have two essentially types of variable. There are actually more, but I'm not going to worry about the others for the moment. So the two main types of variable that you're going to run into in your programming are numeric type and character type. So numeric type is a catch-all for anything that is a real number, integer or otherwise. Okay, in Python, conversely, you have three different types, one of which is the integer, one of which is the float, which is basically a real number, and one of which is the string, which is the equivalent of a character. So a string is not a number, it's a string, like a name or anything like that. Prior to Python 3, this integer and float difference had a series of very, very important consequences. It had a few very important outcomes that with the implementation of Python 3 are essentially no longer there. So for most intents and purposes, or all intents and purposes, you can now consider that the R treatment of a generic numeric value that is a real number and the Python version of a generic numeric that is a real number is essentially true. There is still the labeling of integers and floats in Python, similarly as there is also an integer label that we'll look at in a second in R, but they are mostly labels. They don't actually mean a great deal in the actual context of running the code. And that's because of this thing called dynamic typecasting. And that is how values are converted between various types on the fly when you run the code without you having to do anything. So for example, let's define two integers, nominally integers, in R and in Python, and calculate the ratio of those two numbers. And what we find is that the ratio of those two integers is the numeric value 1.4, right? In Python 2, this action would have given you the number 1, because these are integers, and integer arithmetic dictates that there is no such thing as a decimal point, and therefore this would have the value of 1. And for that reason, integer arithmetic in Python 2 is very, very dangerous for a lot of scientific applications. However, in Python 3, they modified this divisor to dynamically typecast A and B to be real numbers, to be floats. And that means that that particular problem disappeared overnight, right? And so this is what I mean by, for all intents and purposes, you can consider this to be numeric, just as this is, and vice versa. It's entirely possible to well, we'll talk about that in a sec. The way in which you look at the type of variable that you have in R and Python is using this. In R, it's a function called class, and in Python, it's a function called type. And so what you can see is that if I've defined here A is 10, B is 10, and C is the ratio of A and B, in R, all of those things are numeric. And in Python, you have integer, integer, and then the dynamic typecast means that the ratio becomes float, right? You can do the same forced typecasting to integer in R using this as integer function, which means that then we get these classes integer, integer, and numeric. But really, this integer is just a label. Internally, it uses float arithmetic, or actually double arithmetic, so more memory for everything. One of the reasons that one of the ways that we can demonstrate that is, and how this is sort of converged in R and Python to be the same behavior, is using this equality here. So this is saying, is the integer value 10 equal to the float value 10? And in R, the answer is true, because these are both, despite being labeled as an integer, these are both numeric types, and 10 is 10 is 10 is 10, right? In Python 2.7, this equality would give you a false. The integer in Python 2 is not the same as a float, and therefore this would give you a false. But in Python 3, again, they've fixed that so that it now has this equality as being true. And I would argue that this true here makes sense, because the number 10 doesn't stop being the number 10 just because you're counting discretely, right? It's still the number 10. And so this equality, I would argue, makes sense. Cool. The next thing that is important to understand is the difference, and we're going to spend quite a bit of time on this, is about data types. So it's about how you can actually make collections of variables. And so in R and Python, there are a number of ways that you can collect data. In R, we call these vectors, arrays, lists, and data frames. And in Python, they're called NumPy arrays, NumPy ND arrays, dictionaries, and pandas data frames. Here, with the NumPy and the pandas, refer to the packages that these things are inherited from. So like I said, in Python, a lot of these things aren't available in base Python, but they come with these packages that you install along the way. So we're going to go through these each one at a time, and we're going to sort of explain what they are and how they're different, stuff like that. Let me just make sure I didn't forget anything. Good, I didn't forget anything. All right, so first thing we're going to look at is vectors. Now, vectors are something that we should all be pretty familiar with from our maths backgrounds. Essentially, vector is a collection of values, numeric or string. And the way in which you create a vector in R is using this C value here, this concatenate function, right? And so this C concatenate function basically says I want to combine all of the values 1, 2, 3, 4, 5, 6, and then I'm going to print it, and I'm going to print the class of it. And what you can see is that the vector here that I've created from numeric values is a vector, but importantly, it has the class numeric. That is to say that there is no difference between the class of a single number and the class of a collection of numbers in R. They are exactly equivalent. And the reason for that is because R's entire base language is vectorized. That is to say that every single function in base R is able to be used as a vector or as a single value quantity. Now, in Python, that statement is true of all NumPy functions. So in NumPy, we define an array here. So numpy.array. Remember, we imported NumPy as NP. So NP dot is how we access the things that are within the NumPy module in Python. And we want to use the array creation. And then we add actually a list of values, 1, 2, 3, 4, 5, 6. And we then print it, and we look at the type, and we see that this thing has is the vector now, 1, 2, 3, 4, 5, 6, and it has the class NumPy ND array. Now you'll notice that there's this ND that's coming at the front here, which we didn't ask for, right? And that's going to be important in a few minutes. So why that is, we'll explain in a little while. Okay, so as I said, the vector, or rather the numeric or a single value, is actually a special one element case of an n-dimensional array in R. Whereas in Python, a one-dimensional object is a type integer or type float, and a vector of quantities is a type numpy nd array. And it is populated with numerics, integers, floats, or characters. Great. Right. So this ND array here is the reason that this exists is because the vector in Python, or rather the array that I've specified here in Python, is actually just a special 1D case of multi-dimensional arrays. So in Python, if I ask for a one-dimensional vector, it doesn't give me a one-dimensional vector. It gives me an n-dimensional array that has one element or one dimension that is only length 1 long. And the reason that's interesting and important to know is because it sort of signals a distinction or a difference between R and Python in terms of the philosophy. Whereas in R, the single element and the vector are the same class. Whereas in Python, the single vector and a multi-dimensional array are the same class. So there's sort of a distinction between how those two things work, and that might be relevant a bit later on. Let's just show how we can do vectorized arithmetic. So I've created a vector, which is 12 elements long. It goes from 0 to 100. And then in B, I've created a vector that is 12 elements long that goes from 100 to 30. So, counting down. And I then just do some arbitrary arithmetic where I take the sum of a plus b divided by the square root of a squared plus b squared. And I've done exactly the same thing in Python using this linear space command. So numpy.linear space, 0, 100, number of entries 12, same thing for B. And I do this. And what you find is you get the same result in both languages, right? Certainly would hope so. But the relevant thing, or the thing that I want you to take away from this, is that this is vectorized calculation within NumPy and vectorized calculation within base R. So you can do vectorized computation in both languages. In R, it's entirely organized within the base language, and in Python, it's entirely organized within NumPy. And that's important because if you try and do vectorized operations in a different environment which isn't class numpy dot something, then you can run into trouble. So it's good to know. It's one thing to also note, the keen eye will have seen that I've got carets here, little upper chevrons, and I've got star here. Lin space is linear spacing. So it's just, linear steps in the space between 0 and 100, essentially. It's the same thing that this sec just means sequence. Cool. This is not necessarily a typo. That's because in Python, the caret doesn't mean exponentiation, right? It means bitwise XOR, which if you don't know what that is not terribly important, but suffice it to say that it is absolutely not exponentiation. It will spit you out a value. That value might look, if you don't look carefully, like a sensible value, but it will probably be nonsense, or it will be nonsense because it's not exponentiation. So Python, that's basically because of the languages in which these things sort of come from. So this star for exponentiation comes from C, Fortran, etc. And in this caret, you can actually get also from within Fortran, but it is mostly sort of a mathematics term. There's mathematics usage from something like Lisp. You can also do the star notation in R. So if you're worried about converting between the two languages and you're comfortable using star, just use star. But you'll see that I use the caret a lot. So just FYI, if you're going to convert these things. The last thing that I want to point out is the fact that the sum here wraps the entirety of this thing. So I've then taken the sum of all of the values, the vectorized values that come out of this mathematics. Whereas in Python, it's tacked onto the tail here. Why that is going to be very important in a little while, but it's to do with this whole thing I was telling you about object-oriented programming. So we've looked at vectors, we've looked at single elements. Now let's look at arrays. So as I said, the vector in Python is just the special case of an n-dimensional array, so a multi-dimensional array, which only has a single dimension. In R, the opposite is true, right? So the vector is a numeric type and the n-dimensional array is something different again. And the way in which we can show this, so in R, we have this thing which is the sequence that creates the vector, and we can also create an n-dimensional array, which is the same sequence, right? And what you end up getting is here, the vector gives you a vector with 12 elements, and here you get, again, it's numeric type, but it is 12 elements of a one-dimensional array. That's what this 1D means. And the important thing is that these two things are not the same. So if I ask R, is A identical to B, I get the value false. And the reason for that is because of this one dimension thing. Essentially, this thing has, in addition to its elements, has a shape attached to it, whereas this is always assumed to be one dimensional. But of course, with the one-dimensional, even if you have this distinction between 1D and vectors, so a one-dimensional array and a vector, the arithmetic stays exactly the same. You actually don't change anything in terms of actually how you use these things. It's basically a bookkeeping thing within R. And the reason it's there is something we'll see in a second. There's a two-dimensional, when we step up now from one-dimensional arrays to two-dimensional arrays, we get a special class that exists within R that's called the matrix. This is something that you'll all be familiar with from mathematics. A matrix is just a two-dimensional array of values. And it's essentially just a special case of the two-dimensional array. So I can specify a matrix by saying matrix and then giving the number of rows and the number of columns. That's no different than specifying a two-dimensional array with dimension 10 and dimension 5. So it's still a two-dimensional array with the same thing. And in fact, when you do this, when you specify a two-dimensional array like this, R actually does a solid for you and converts it to type matrix, right? So if I look at the class of A, I get matrix and array, and the same is true of B. And in fact, these two things are identical, despite having specified them in a different way. The main reason that there's a distinction between, or that this has an additional class matrix, is because there are a number of functions that are used in mathematics that operate specifically on matrices, right? These are all of your matrix multiplications, all of your complex functions and decompositions of matrices and things like that. And so it makes sense for R, which again is a statistical analysis package, a programming language, to have a special class that means that if somebody feeds a particular thing, B, to a function, it can just say, I'm expecting a matrix. Do I have a matrix? And that's essentially why this thing exists, this class. It's basically a way for R to very rapidly vet whether or not inputs to functions are the correct type. It's also because the back end of R, as I said before, is a lot of C++. And that means that you can basically say, I only want to send things to the C++ code if I'm certain about its form. And the matrix allows you to give you a very strict sort of thing. Okay, in Python, you can generate two or more dimensional arrays using a bunch of different techniques. So here we've generated an array, a two-dimensional array that's of size 10, 5, and filled with ones using this numpy.ones. Here we've done it filled with zeros, numpy.zeros, again, just does what it says on the tin. And here we've done it with numpy nd array. The caution is that this thing gets filled completely arbitrarily. It gets filled with completely random values. It doesn't have necessarily a sensible value for anything, because basically what this is doing is it's sequestering a certain part of computer memory. And that memory can have God knows what in it. So, here there be dragons, caution. If you want to generate an array, a multi-dimensional array, which is initialized with some set of values, this is a very, very common thing that you want to do in R and in Python. In R, you just use the array syntax or indeed the matrix syntax. Here I'm using it. Here I'm generating a 3-dimensional array with dimension 3 on the first axis, 5 on the second axis, and 2 on the third axis. And I want it to use the values from 0 to 1 with 12 elements. So that is not an integer number of any of these sort of sides, right? So that's important. And basically what I can do is I can generate an array by just saying I want to have an array, I want to fill it with these values, and I want it to be that dimension. And what R does is it just recycles these values again and again and again and again and again and again and again until the entire array is filled. At which point you end up with something that looks like this. So if I then print A, then I end up with something that goes, so you can see that what I'm doing is if I look at the first slice in this dimension, it's a 2-dimensional array of length 5 and 3, and it has values 0, 0.9, 1.8, 2.7, 3.6, 4.5, da, 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 until I get to 1, and then it recycles it, 0, 9, 18, etc., etc. And it recycles it onto the next layer as well. Okay? In Python, you can't do that, right? It's fundamentally not possible. And the reason it's not possible is because the main way in which you create a n-dimensional array that is initialized with a set of values is you define a vector, a one-dimensional array with those values, and then you reshape that vector into the n-dimensional shape that you want, right? And what that means is that if you try and do it, but you say, I want to take a thing that is 12 elements long and convert it into something that is 30 elements long, then it's going to say, no, you didn't give me 30 elements. I can't do that, right? And so you cannot reshape an array of size 12 into shape that, right? You can do it if you can do this sort of recycling thing if you want by being a bit cheeky and defining the thing you want to recycle and then concatenating that thing a certain number of times. And if that concatenated thing fits perfectly into the 30 elements, then reshape will work. So this is now 10 elements, not 12, and then reshape will work. Conversely, you can do, and that is sort of the close to the R reshape. Sorry, the R recycling, right? Another way you can do this is using the repeat function. So you can say, I want to create a vector of length 10. I then want to repeat that vector 3 times. So I have 30 elements, and I then want to reshape that 30 elements into the shape that I want. And so both of these work, but they give you something that looks different from one another. So in the first case, you end up with something where you've got 0 to 1 on each layer, right? 1, 2, 3. And in the second one, you end up with something that looks different again. So I've asked, do all of the A's look like the R version of B? And the answer is no. And I said, okay, I said, does this look like what I generated in R? The answer is no. Okay, does this look like what I generated in R? And the answer again is no. And that sort of goes, well, why? Why does that not look the same? And the reason is because of the way in which the array is being filled in the background. Say if you have a cube of entries, whether you fill it this way first, or this way first, or this, or whatever, the other way, this way first, matters, right? Now, R is doing one thing in particular, and Python in both of these is clearly doing something else. So it's important to know how your arrays are being filled if you want to make sure that you don't accidentally make a mistake later on. And turns out the reason why it doesn't agree is because Python has a backend or a history in C, and it follows a lot of the conventions of C in terms of how it fills arrays. And so when I do this reshape, what I'm implicitly saying is I want you to take this vector, this long one-dimensional vector, and I want you to reshape it in the C convention. So going this way, say, and then this way, and then this way, into this shape. But R uses a different convention, which is known as the Fortran convention. Basically, the difference is that in the C convention, you iterate the first element the quickest, and in the Fortran convention, oh wait, I'm going to get this the wrong way around. Yes, in the Fortran convention, you iterate the first element the quickest, and in the C convention, you iterate the last element the quickest. So you cycle the last element. And so if we tell Python, no, I specifically want you to fill this thing like Fortran did, then all of a sudden everything is happy, and we end up getting something in Python that looks the same as what we had in R. So that's how you need to be careful of doing this sort of a reshape. That's just a possible trap for new users. Of course, provided you're using Python for Python and comparing Python things to Python things and comparing R things to R things, this really doesn't matter a great deal, right? As long as you know what the convention is there and you're consistent. But if you're combining things across the two different languages, then this can be important. Okay, the next thing we're going to talk about is lists and dictionaries. So Python and R both have the functionality to use lists. Lists are really important. They're super flexible. They're super widely used in basically all programming languages. And that's because a list can be a combination of any other set of data types, right? So for example, in R, I can create a list just using this list function. And my list, my first element is called A and is filled with this n-dimensional vector, this n-dimensional array that I just generated down here, this thing. B is the n-dimensional array that I called B. I'm then going to make a vector, and I'm going to call it vec, and then I'm going to make a string, and I'm going to call it str. And then I'm going to look at the structure. str in R means structure. So I'm going to look at the structure of my list, and you can see that I have a list of 4 elements. They are A, three-dimensional array, B, a three-dimensional array, vector, a vector, and str, a string. In Python, this is slightly different. In Python, you generate lists using square brackets. And so I can generate a list like this, where I can say, okay, I want my list to be A, B, this vector of quantities, and then this string here. And I look at it and I get, yes, my first element is this multi-dimensional array. My second element is my second multi-dimensional array. My third element is my vector, and my fourth element is my string. You can also define this thing called a dictionary. And in dictionary, you specify these things by name. So I want to name the first element A, and I want to give it this thing A. I want to name the second element B, and I want to use it B. I want to name this thing vec, and I want to create a vector, and then I want to name it string, and I want to fill it with a string. And then if I print this dictionary, what you find is that you have this thing named A, and that's what it's filled with. I have this thing named B, and that's what it's filled with. I have this thing named vector, and that's what it's filled with. And I have this thing named string, and that's what it's filled with. So just to answer the question that's here, does str stand for structure or string, or is it the same? I realized only as I was saying this that I've unnecessarily complicated this by calling that str. The function str is the structure function, and it prints the structure of the thing that is within the brackets. I've named it str here to mean string because I was being daft and I shouldn't have done that. But yeah. The important distinction between the R list and the Python list and the Python dictionary is that the Python list is numerically referenced, so referenced by number, And the Python dictionary is referenced by name exclusively, right? In R, lists, which function effectively as both dictionaries and lists, can be referenced in both ways. So for example, in Python, if I want to reference my list, I need to use the number 3, and that gives me, this is my string. If I want to use the dictionary, I need to reference it by the name, str, and I get my string. But if I try to reference my dictionary by 3, I get an error. And if I want to try and reference my list by the name str, I get an error. Conversely, in R, the list forms both functionalities. So it is both named and numbered. And so I can say I want my list and I want element number 4. I can say I want my list and I want element str. And I can also use attribute syntax. So I can also say I want my list and I want you to give me the thing which has got the name str. So this $ here is similar to the Python dot. It is basically saying, I want you to look inside this thing and give me that. And so this works in all things. So it's worth, that's what I just said. So lists are super useful. And the main reason they're useful is because you can feed lots and lots of things to them that can be arbitrary types, and that works. There is one very important thing. It's a special type of list in Python that's called the tuple. And the tuple is essentially an uneditable list. So it's referenced by number, as a list is, and you can't edit it once it's been defined. And the reason it's so widely or important to know about is because it is used almost exclusively when functions return things to a main script. So tuples are defined using just normal parentheses. And I'm going to define here a tuple, which is a 2-dimensional array, a string, and a number. And I then look at tuple, and it comes out as this 2-dimensional array, my string, and my number. But in Python, you can also declare a tuple without these parentheses. So long as you have commas separating, that will give you a tuple. So here I can do the exact same thing without the braces, and I end up with the exact same tuple. Well, here I've created it 3 by 3 and changed the name so that you know that it actually got changed. But once this thing exists, you can't change it. So if I try and assign modified to my string here, then I get this tuple object does not support item assignment. So once this thing is created, you cannot change it, right? It's uneditable. But the reason why they're so widely used is because most functions in Python return tuples. They return uneditable things. And the reason that they return uneditable things is because tuples have this really unique property of being able to be unpacked. And what that means is that if I have a tuple on the right-hand side of an equal sign and a left-hand side of an equal sign, then Python will unpack the right-hand side into each of the variables that are separated by commas on the left-hand side. So here, my function returns a 2D array, a string, and a number. And I've run my function, and it returns this tuple, which then gets assigned to the matrix goes into mat, the new string goes into new string, and the value goes into value. And you end up with this. If I print what is new string, I have this new variable new string that is filled with new string. Okay? However, it's super important to realize these things are referenced, again, tuples are referenced by number. And the unpacking assumes numeric ordering, right? So if I was to run my function and accidentally say the first element is new string, the second element is matrix, the third element is value, then I will get new string being assigned to the matrix. And so it's very important that you know the ordering of the return of your function when you're doing this dynamic unpacking. Okay, so just to very, very a little trap for young players. This positional unpacking is everywhere in Python. It's basically fundamental to what is known as Pythonic code. So this sort of a thing is very, very common. So you can use this sort of positional unpacking with R as well, but basically it never happens. And the reason it never happens is because R is always prioritized named returns. And that is to say that when a function returns something like this in R, you will get a list, and that list will have names that are called matrix, string, and, or, whatever you want, whatever the person who wrote the function named them. So this could be, covariance, this could be status, and this could be value or something, right? So, but returns in R are almost always named, and so this positional unpacking never happens, basically. Okay, the last thing that we're going to look at, the last data format we're going to look at is called the data frame. And the data frame is something that exists in both R and Python. And in Python, it exists within this thing called pandas, this package called pandas. And the way in which we're going to look at Python packages data frames in R and in Python is by using a little another thing that I wanted to show you, which is about default data sets. So in R, and we're going to use these quite a bit in this course, there's a lot of data sets that just exist for you to use. So numerical data sets containing lots and lots of things. So which probably tells you a little bit about myself, I'm going to use this hitters thing, which is the Major League Baseball data from 1986 to 1987. And so what we're going to do is we're going to get the data of hitters, and we're going to put it into this data frame called df. And we're going to take a look at the first 4 columns of the data frame. And the first 4 columns contain the rows of the data frame are named. So they're named rows. They have the names of the players, the number of times they were at bat, the number of times they hit the ball, the number of home runs they had, and the number of total runs that they made. You can then also create a pandas data frame. So here I'm importing pandas as PD, the same way that we did for NumPy. And I'm going to define a pandas data frame. And just for simplicity, I'm going to tell it to use the R data frame because we already have it. And if I look at it in Python using this data frame.head, which is basically the same sort of thing that I did here, you end up getting the same stuff. So we have the 2 things now exist both in R and in Python, and we can look at them both. So important things about data frames. So data frames are named in both columns and rows, or can be named in both columns and rows, and you can access them by name or by index. So like the lists in Python, in R, you can name them, you can reference them however you like. So I can reference the 141st excuse me, row of the data frame here in R, which is just a random name, Jose Canseco. Don't know why I would have picked that one. And you can reference it by the row number and the column I can reference by name here. So I've referenced the 141st row and the home run column, and I get the number 33. Or I can do the opposite. I can reference the row by name and I can reference the column by number and I get 33, or I can reference both in the same way or both in different ways. So it's totally flexible. And a similar sort of thing happens in Python, albeit slightly differently. In Python, you can reference rows using numbers with the iloc function. And I want to pull out row 82 this time, and that's a guy called Don Mattingly. Again, just totally random name. Don't know why I picked him. And again, we can then look using numbers and iloc at the row 82 element 2, and that gives us his number of home runs. Or if we want to reference by name in data frame, in pandas data frame, we have to use the loc, not the iloc, and that gives us the same element. You can't co-reference in mixes of strings and numbers here. You can if you chain them together, I think, but that's not really relevant. You can also reference by attribute pandas data frames, just like we did in the list. So you can say, I want to look data frame and then the home run column, and I want number 82, and the same thing here. Data frame, home run column, 141, etc., etc. You can then also subset. This is really useful. So you can subset things by, just using a logical statement. So if I want to pull out all of the entries in my data frame where they have more than 30 home runs this season, then I just do data frame access home run is greater than 30, or similarly, data frame location home run is greater than 30. And in both times, I get the list of names of people who have more than 30 home runs. You can make this logical explicit. So this returns actually true, false, true, false, true, true, false, 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 true, false. You can actually then get this to be indexes, so 1, 5, 12, 151, by using the which function in R or the where, numpy where function in Python. But of course, if we use numpy where, this doesn't become a location anymore. It becomes a number of locations or an index. And so index, you have to change this to index log. Whereas in R, that stays exactly the same. Okay. You can then do lots and like data frames are super powerful because you can do lots of arithmetic on them. You can basically calculate values and different things. So I'm calculating the average run rate or the ratio between run rates of people in the top half and bottom half of the number of hits per season. And it turns out that if you are in the top half of the hitters, you tend to 20% more often get to home plate, which kind of makes sense if you know anything about baseball. And you can do exactly the same thing in Python, albeit you can't do it necessarily in, oh no, you can, I think, do it in one line in Python, but I split it over multiple lines because it looked a lot cleaner. One of the things about, one of the hidden things about R, and which is really useful, is this, that data frame has an additional library attached to it, or you can attach to it, called data table. And the secret of data table is that it is blazingly fast for doing computations. So just as an example, if I take a data table, which I've used here, a different data set that is all about flights, domestic flights that flew into New York City in 2013. Again, it's just a generic function. Data table computations are extremely quick to work on huge data sets. So if you're working on large data sets, it's worth pointing out here that, you know, data table is so fast that for large computations on, so doing an assignment on like a itemized assessment of values on a 50 gigabyte size table in data table is more than a factor of 2 faster than any other means of doing it in any language that exists ever, like at all. You know, including C, C++, everything. Like this is blazingly fast at doing these things. For reference, the pandas data frame doesn't actually do anything in this. It runs out of memory. If we go to 5 gigabytes, then yeah. So the data table here does this 5 gigabyte file in 15 seconds, whereas pandas does it in of order, you know, 2 minutes, a minute and a half. So that's just to show you that it's very, very rapid. And in fact, we can test this ourselves, which is basically what I've done here. I've just benchmarked the computation of the mean arrival time of airlines according to you know, when they arrived and when they departed, according to the carrier. So, you know, United Airlines, All American Airlines, et cetera, et cetera. And data table can do this computation on average in 13 seconds for the entire data set, and doing exactly the same computation in pandas takes on average 17 seconds. So the fastest part of the fastest version in pandas takes on average the same as the average version in data table. So it's just suffice it to say that it's very quick. Okay, we have 7 minutes to go. There's a lot. We're definitely not going to get to the end of this in the next 7 minutes, but the next thing is super, super important. And it's also kind of a little bit interactive, a little bit fun. So I want to do this first. Before we go into the next thing, I'm going to ask you 2 questions, 2 polls. These are going to seem probably very, very, very weird and random, but I think it's worth asking them nonetheless. So this is the first question that I want you to answer. So we have the U-Bahn to Rub arrives at your stop, and you enter the door nearest to the driver and sit down at the first chair that you see. Your friend, who is about to get on at the next stop, sends you a message asking, what carriage are you in? What do you reply? Do you reply with that you are in the first carriage, the 0th carriage, or you reply, new phone, who's this? Okay, getting there. 9, 11. Wait for a few more. And I'm almost certain that I know who wrote the 0th. And cool. All right. So overwhelmingly, people would say the first one, which I think makes sense. The first carriage is the thing that you would get into, right? The second question that I want to ask you is this one. You live on the top floor of an apartment block. To get to your apartment, you click the elevator button marked 4. How many floors or levels are there in your building? Let's assume that there's no basements, just for all intents and purposes. Okay, this one is much more one-sided. Okay, so everyone here is saying that there is, well, the majority of people are saying that there is 5 floors on your building. Okay, that's really good to know. All right, I'm going to close that poll now. The reason I just asked you those 2 things is because the next thing that we're going to talk about, and probably the last thing we're going to talk about, is what's called indexing. And this is how elements are referenced in arrays and vectors and all that sort of stuff in R and in Python. And you can't avoid this. This is something that you are going to have to recognize and understand and deal with. R objects in the R language are what are called 1-indexed, whereas in Python, they are what are called 0-indexed. That is to mean that in R, if you take a vector, which here we've given the letters A, B, C, D, E, and I say, what is the first letter? The first letter is A. Whereas in Python, if I make the same question, I make the same array, and I say, what is the first element? The first element is B. And that is because the first thing that exists in a Python array is the 0th element, not the first element. Okay? Obviously, if you look at this, and this also means it has important impacts for the end of the array, where you have length array is equal to E, or length array is equal to 1 minus the length is equal to E. This is super important, right? It causes lots of bugs if you do it wrong. But the reason it exists is actually pretty simple. And that's because 1 indexing, or first element indexing, is to do with counting. So as we said, when you have the train arrive, the first carriage arrives, the second carriage arrives, the third carriage arrives. This is counting carriages, 1, 2, 3. With 0 indexing, you're not interested in counting, but instead what you're interested in is offsets. So what you're looking at is, how far am I from the first thing? And if you are the first thing, well, you are 0 elements from the first thing. Then you are 1, then you are 2, then you are 3. And this is where the levels in your apartment block come in, right? Because what do the levels on the elevator actually mean? They mean 1 floor away from ground, 2 floors away from ground, 3 floors away from ground, right? So the difference between 1 indexing and 0 indexing is to do with whether you are counting on one hand, or whether you are looking at offsets on the other hand. Python is fundamentally based in the offset system, whereas R, being about mathematics, is fundamentally based in the counting system. Offsetting is mostly to do with how things are stored in memory, and so is very important for computer code, right? So C is very fundamentally offsetting, right? Whereas, mathematics, we count things. We don't start counting from 0. There's a lot of stuff in here about what impacts that has in terms of indexing, in terms of negative indexes and how they're interpreted in both of the languages. In Python, a negative index refers to the end of an array. And that's really natural when you're doing offsetting, right? Because if you have -1, 0, and 1, you're saying, I want to take the -1th element, or -1 elements away from where I am, which if you loop around ends up being the last one. And so you can do 0, 1, 2, or -1, 1, -1, 0, 1, and you end up with this behavior in Python. If you do the equivalent thing in R using negative indexing, you get something totally different, because in R, with its 1 basis, negative indexes are actually deletions, right? So if I specify I want to I have the -1th index, it deletes the first index, right? And that's really important. We've hit the hour, so I'm going to stop there. We've still got quite a few bits and pieces that we will, well, actually not too much. We're going to be looking at object orientation next week at the beginning of the lecture, and just reading and writing and plotting data. That'll only take sort of 5-10 minutes. And then we'll get started with the main thrust of the course. So that's pretty much all we've got for today then. Thank you all for attending. And if you have any questions, then this Slido will be open for the remainder of the week. So you can put in questions whenever you like, and I'll have a look at them and I'll try and answer them at the beginning of next week. Great. Thanks very much, everybody. And I'll see you all in a week's time.
Sorry, Angus.
Yes.
Can you maybe say something about the question for after the lecture?
Yes, I can indeed. Do we have exercises together or work on alone? What will the exam be? So there aren't currently exercises. However, the lecture notes are written in such a way that if you want to run them like you would run a piece of code, you can actually do that. So you can copy and paste snippets of code and stuff and do these things. But if you want to actually try out exercises, there's no formal exercise class for this course, but I'm happy to put together little exercises for people if they think that would be useful and interesting. And to answer the second question, it kind of depends. This lecture, there was a lot in there, as you can probably tell. And so it was important, I think, to use the full 2 hours. I know 2 hours being talked to is a very, very long time. And so I'll try at least sometimes to have a break in the middle, so that it'll be less than the full 2 hours. But the course will go from starting at 2 until 4 on most weeks, yeah, with probably a break in the middle. If that's difficult for everyone, because I know that in German lectures it's frequent for people to start at 1/4 and to end at 1/4. If that's super important for people, then obviously I can revisit and we can change that. But just let me know. And any feedback in the questions or on Moodle or just directly emailed to me is happy to be received. The exam. So the exam for this course is going to be just an oral exam. So if you would like to take the examination for this course, so it's going to be if people have taken some of the other the astronomy courses, we tend to do a lot of oral examinations. So it'll be the exam will be oral for this course.
Okay, thank you.
Great. Cool. Thanks very much, everyone. If you have any more questions, then please feel free to add them to the Slido. Otherwise, we will see one another in a week's time.
Thanks. Bye.